Hello again, and let's get started with the second part of our first chapter, which is about water distribution, amount of the water on the Earth. In this lecture, I will talk about water distribution in space and time, water balance, catchment, and we will have some examples to practice what we learned in this lecture. In previous lecture, we talked about hydrologic cycle and we saw that the amount of water remains constant on the Earth or globally scale. But we didn't talk about the distribution of water at different locations or distribution of water with respect to the time. So in this lecture, I first talk about where is the Earth's water? Where is the Earth's water? Do you have any idea? At least you know that most of the Earth's water is on the oceans or in the oceans, yeah? Previous video we watched together said about 97% of the Earth's water is in the oceans. Okay, now 95%. Do you know that oceans are saline, not drinkable? Therefore, 96.5% of our Earth's water is saline. How about the other water storages, water reservoirs? Look, in this table, taken from Wenti Cha, shows the amount or volume of water, Earth's water, as well as its percentage that estimated for the globe. The estimates of the total amount of water on the Earth and in various processes presented in the table. As I already told, 96.5% of water is in oceans. So it is not fresh water, it is not drinkable. So the remaining, only 2.5% of the water of the Earth's water is fresh water. A small segment of Earth's water is fresh water. How much is it? 2.5%. So in table, if you look at the table, the biggest part is ocean, 96.5%. After oceans, the biggest storage of water are ice caps and glaciers, which covers 1.8% of total water of the world. And the last column here shows the percentage of water or reservoir. These are called water storages or reservoirs. How much of this reservoir constitute how many percentage of fresh water? So you see that approximately 70% of the available fresh water is from glaciers and ice caps, far from our use, yeah? Look, the fresh water is only 2.5% of the Earth's water. And from those small 2.5%, 70%, approximately 70% is glaciers. So think about how small, the volume of fresh water is small. And the other reservoir could be groundwater. We have also saline and fresh groundwater separated. And in this column, you see that, for example, fresh groundwater which is the main water, so fresh water for humanity, the main fresh water for humanity is only 0.76% of the Earth's water. And lake waters, fresh lake waters, very small percentage of the total water, and less than half percentage of the fresh water is comes from lakes, and so many other reservoirs. So these are main water reservoirs. And in this graph, the comparison of the percentages of different reservoirs shows more meaningfully. Look, from the first column, it shows total global water. From the total global water, as I told, 96% is in oceans, and 2.5% is fresh. And also, there are some other saline water, like saline water in the lakes, that constitute a small percentage of the Earth's water. From these 2.45% fresh water, as already discussed, glaciers create 68% of the water. Again, is not accessible, easily accessible to use. And this part, groundwater and surface water, like water in lakes, fresh water in streams, are accessible to human use. Therefore, accessible fresh water is 30% of 2.5% of entire water. And about surface water, if you look about first surface water, 70% of our first surface water is on ground, is ground ice and permafrost. I will talk about this definition. What is the ground ice? And permafrost means underground ice. And in lakes, we have 20% of our fresh water are in lakes. Then the other smaller water reservoirs are swamps, marshes, rivers, and living things, or biotic, as I told, human, trees, plants, and animals. So we can conclude also the total amount of water that we have in hydrological cycle is about 1.4 million kilometer cube. 1.4 billion cube kilometers. Any question? So this is the amount of water that we have, and we talked about their spatial distribution. In that column, in that table, we talked about swamps, marshes, permafrost, and also snow patch, which is really insignificant, but it is a reservoir also. At the same time, it is a reservoir. So what is the difference between swamp and marsh is clear in this figure. Swamps and marsh are both wetlands. We say wetlands. So swamp is a kind of wetland that has trees or permanent forest, permanent woods. In that case, this is called swamp. But marsh are smaller, generally are smaller than swamps without permanent trees. There are only herbs or bushes which do not have roots or permanent roots on the ground. In that case, we say it is marsh. Marshes are commonly created next to the lakes, but swamps are bigger ones that created along the large rivers. For example, think about Amazon jungles full of swamps. So what permafrost, as I told, we have glaciers under the soil or above the soil. Permafrost is the frozen soil, as you see here. The frozen soil which remains frozen for a long time. And commonly, this kind of locations happen at polar region, Nordic countries like Norway, Finland, or highlands of Sweden, and also in Canada. So snow patch is, as you see, the remaining. You saw such phenomena in your own country. After the day is, we have a sunny day, but there are still some places that snow patches. Those snow patch, what's its role in hydrologic cycle? It keeps the soil wet. It keeps soil moisture, provide soil moisture for a long time, and also contributed in the evaporation system of component of hydrologic cycle at local scale. So now let's talk about water distribution in time. Water distribution in time. To talk about it, we should talk about residence time. Residence time can be defined for any substance. But for material flowing through a volume, the residence time is a measure of how much time the matter spends in it. Examples include fluids in a reservoir, water in a catchment, and drugs in human body. For example, you drink one drop of a drug, and you see that you know that its residence time in your body is maybe 8 hours, and after 8 hours you should drop the second dose, because the residence time in your body is 8 hours, for example. Or resident time of this is not a good example, but it gives some concept about residence time. Think that you charged 1 liter gas or 1 liter gasoline in your car, and with those 1 liter you can drive for 10 hours. Therefore, residence time of that 1 liter gas is 10 hours in your car. Now, as a hydrologist, we work with reservoirs. What does the reservoir mean? Don't forget, here I showed you different reservoirs. Ocean is a reservoir. Ice caps, stream, dam reservoirs, or even catchment or watershed. What's the catchment? We will talk more. Is a reservoir, or you see any tank, any system that has some input water, has some output water, it's called reservoir. Hydrological cycle. I showed you a picture of one part of a landscape. It had several reservoirs, groundwater, ocean, lake. These are all reservoirs. Okay, how much time or duration of a time that water remains in that reservoir is called residence time. Now, how we calculate residence time? To calculate residence time, we use this formula. Residence time, the formula comes from its definition. Water molecule, for example, or mass remains in a system. Okay, to explain more, let's see first this figure, for example. Here we have a tank. Here we have a tank, and we have a permanent input or release input into the tank, and we have also some water goes out of the system, out of tank. The first thing that I want to ask you, in the beginning, please contribute, please answer. Assume in the beginning the tank is empty, full of nothing. And you open the valve and water comes into the tank. Do we have water output from the system? No. At first, there is no output because the water should gathered, collected in the tank up to reach the level of the orifice. It is called orifice, the level of the location of outlet. Then we will have some release from the system or output the system. And if the amount of or discharge or flux of input is higher than the flux of output, what will be happen? The water level increases and we also have the output. So in case that we have input to the system, we have output from the system, and we have a constant level of liquid, level of water in the tank, it is called steady state system, a steady state system. What does it mean? It means that when the level does not change, it means that the amount of water input per unit time or per time is exactly equal to amount of output, yeah? What comes in goes out for the given time. Therefore, there is no change in the elevation of water. What comes in per unit time or how much water comes per unit time in terms of mass of water is called flux. F is called flux in terms of mass. M is mass of water and T is time. Therefore, flux is mass per unit time. Now we know the concept of steady flow. Now we know that the system, our system is steady state. Okay, there is steady state means no variation at the elevation of the water in the tank by time. The elevation is constant. So you need to calculate or to find residence time. Okay, now assume one water drop entered into the system and passed through this random location, which is called pass line, and then went out. This drop went out, maybe after 10 seconds, 15 seconds. Therefore, residence time of that droplet is 10 seconds. Different droplets may pass different locations and may have residence time of different with the previous one. Maybe 10 seconds, the other 11 seconds, the other 12 seconds, the one 8 seconds, because the pass is random and one can be in average. We can say, for example, the average is 12 seconds and residence time of water at this small tank is 12 seconds. Mean residence time or average residence time. To calculate it, if you know the flux of input, which exactly equal to flux of output, you can just extract T is the residence from this equation, because you know the flux, T equals to mass divided by flux. Here, this is the same thing, but not only for water. Everything, as I told, for every system, which we say our control volume, if you know input and if you know output, you can find residence time for steady state condition, because the input and output F are the same. Is it clear? If no, I will talk a bit more about it in the next How many questions? So you will see in this table that residence time calculated for different reservoirs that we already talked about it. The residence time is the average duration for a water molecule to pass through a water body. A water body is a reservoir. It can be derived by dividing the volume of water by the flow rate. You know, flow rate or flux or discharge, you will hear frequently in this lecture. But just after several lectures, I only use discharge, the term discharge. Flow rate means the amount of change of water by time. When we are talking about rate of something, rate of increase means how much something increase by time, okay? So flow rate, in previous slide, we said flux, yeah, for flow rate. We said flux. When we say flux, it means change in mass. But when the mass of a substance change, its volume change can be changed. Okay, its volume is changed. For example, instead of saying 2 kilograms of water, you can say, for example, 0.5 cubic meter of water. And generally, we in civil engineering, we deal with the volume of the water. Therefore, instead of change of the mass, we can say change of the volume of the water. If we talk about volume change, volumetric change, it is called discharge, not flux. So this is the difference between discharge and flux, but both are the same thing. One shows change in the mass per time, the other, or discharge, shows change in the volume per time. Both are flow rate, and estimated residence time for different water bodies are shown here. You see that for oceans, residence time are about 2016 to 3,200 years. For glaciers, about 50 to 100 years. For a seasonal snow cover, 2 to 6 months. Soil moisture, 1 to 2 months. For shallow groundwater, for deep groundwater, for a lake, for a river, for atmosphere, several days. For rivers, residence time or average residence time for rivers is 2 to 6 months. Who can explain this a bit more? What does it mean? Residence time is about 3 months in a river. Can you explain, Arda? Arda Shavata, you are enjoying nature.
Hello, sir. What did you say? Can you repeat again?
You didn't hear? Okay. Explain to me what when we say
your voice is lagging, teacher, for me.
Okay. Now listen. I said that residence time of water in a river is 3 months. What does it mean? Explain a bit more.
Alabilirsiniz, evet. I don't know, sir.
Good, thank you. Nice answer. Kemran Bey, can you give some idea about this sentence?
Görüntü dondu bende ya.
Kemran Bey Arfoğlu. Yeah, residence time of a river is 3 months. What does it mean?
I have no idea.
One of you, okay, Cameron, please turn off your microphone. Maybe there is noisy. Okay. Who want to answer? It means that when we say residence time of water in rivers is 3 months, it means that all water, it means whole water under that river removes from the river each 3 months and then come back to the river. Either one molecule or entire water. So when you see the river after 6 months, because due to the length of the river, it varies between 2 to 6 months, but the maximum is 6 months. For example, for Amazon, for Mississippi, for the Nile. After 6 months, when you see the Nile in different 6 months periods, the water that you see in that river entirely has changed or already circulated at the water cycle and then came back to the river. And this is important to us, residence time important to us for different reasons. For example, when we assume that a kind of pollution releases to a river, but in a steady state, not for a short time. Steadily, a kind of pollution releases to the river. That pollution remains 6 months in that river. This is definition or usage of residence time. How we calculate? Either by mass per volume, by mass per flux or volume per discharge. If you have mass and flux, you can find it. If you have volume and discharge, you can find it easily. So based on the definition that I showed you, please solve this question, read it, and solve it in 2 minutes. Let me help you when you are solving. The volume of atmospheric water is, okay, volume is given atmospheric water. Therefore, the water body is atmosphere, is blah, blah, blah. The evapotranspiration from land, output from land, is this value, and output from ocean is the other one. Estimate the residence time. What was the residence time? Is volume per unit time. And if you want to find the volume, residence time is volume per discharge, you need to calculate discharge first. And discharge means how much water went out of the system. You see that we have evaporation from oceans and also evaporation from land. If you gather, it is entire output, and the input of the system, which is the atmospheric water of the system, volume of the water in the atmosphere, given as here. So by dividing those two values, you will see that it's about 0.02 year, and multiplying by the number of days in a year, it gives you 8 days. Therefore, residence time of water, atmospheric water in the atmosphere is 8 days. And This is why written here 8 days or days, and one example shows 8 days. So we understood that water distributed at different reservoirs, spatially distribution of the water is called. And for the temporal distribution, we said that at each of these water bodies or reservoirs, water remains for a certain time and then transform to another phase. For example, at atmosphere, 8 days, at river, 6 months, at groundwater, several years, at the oceans, hundreds of years, for example, but finally finally leaves that body and enters to another component of the water balance or water cycle or hydrological cycle. And what is here important is that the amount of water, as I told, amount of water at the beginning, from the beginning, I'm saying amount of water in the hydrological cycle on the Earth is constant, and it's about 1.4 billion. We calculated, estimated 1.4 billion cubic meters. Okay, so what does the water balance means? Means nothing than I said. Water is constant, or it changed from phase to phase. It changed from time to time, from location to location, but its amount at global scale is constant. The total amount of water available to the Earth is finite and conserved. Also, the total volume of water in the global hydrological cycle remains constant. The distribution of this water is continually changing on continents, in regions and local catchments. The global annual water balance is presented in table 3 of your book. And here you see that I highlighted the word conserved. Actually, water balance, when we are talking about water balance, its concepts comes from principle of conservation of mass. Water balance is we say that amount of water is constant. Okay, we already in physics said the amount of mass is constant. Yeah, this is conservation of mass, and you have heard it. So to this concept of water balance is used to solve so many problems in hydrology and to do so many designs. For if I gave the example of GAP, Great Anatolian Project, and so many designs in that project, this is the base. The project is based on water balance, where in the Anatolia region. Now, Anatolia region, for example, Eastern Anatolian region, or any land, atmosphere, and all the ground that contributed in the water, even underground, in that project can be considered as our control volume to calculate water balance. And based on water balance, we can do some designs. So let's go more in detail about water balance, conservation of mass, and extract a formula that we will use to calculate water balance or in small control volumes. As I told, here you see that this is conservation of mass. Mass input or mass into the system equals to mass goes out from the system plus change of mass stored in the system, like previous tank. Assume that at the first, this is my control volume, an imaginary volume, for example, Anatolia region, for example, your city. There are some inputs in terms of precipitation or inputs by water inputs by pipelines, by canals, comes to your city or to my imaginary control volume, and it would be some storage. You see change. It would be change in the amount of mass. If you have already water, okay, it will be change, and finally it will you will have some outputs or some mass outputs from the system. And based on conservation of mass into the system equals to mass out of the system plus change of mass is stored within the system. But this is physically definition of the conservation of mass in physics. In hydrology, instead of mass, I said we use volume, water volume. The same formula is this. The volume of water input to the system, now it is water, equals to volume of water goes out of the system. O means out, I means input, plus delta S, or plus the change in the storage, volumetric change into storage. This is nothing than conservation of mass. Okay, conservation of mass. If you take derivative of this equation with respect to time, or if you divide, we can simply say divide both sides by time, or you consider entire process in a given time of delta t. What you will have Vi over dt minus output volume over dt equals to rate of change of the storage by time. Today I said that dividing something by dt or thinking about variation of it by time, it is called rate. Yes, it is called rate. So rate of input volume minus rate of output volume equals to rate of change in the storage. Rate of volume in hydrology and fluid mechanics is called discharge. Yeah, rate of volume, change of a volume by time, rate of volume. It is called discharge. So you also show the rate of change of volume by Q. Here we show discharge always by Q. Therefore, the conservation of mass could be written in this form also. Input discharge minus output discharge equals to rate of change of storage. Rate of change of storage at the given time, or the time you consider. Okay, now I have a question. I already defined steady state systems. Who remember it? What is the steady state system?
When input and output amounts are equal, then we can call that system a steady system.
Yeah, it is a steady state. There are other also, there is another definition also. Think about the tank and water level. In steady state, what will happen on the water level? Jaren, continue please.
It will never change.
Yeah. The level is constant. What does it mean? It means storage is constant.
Constant, yeah.
Therefore, delta S over delta T should be 0, yes? And the delta S is storage, change in the storage, rate of change is constant, or, sorry, no change, not constant, no change means 0. So at steady state system, you can say that input discharge equal to output discharge. You already said. Why? Why? Because ds over dt is 0. Because this is 0, therefore, input discharge equals to output discharge at steady state system. Do you agree that hydrological cycle, water cycle on the Earth is steady state? Globally, yes. I told delta S, storage water is constant. The amount of water in global is constant.
But if we consider like a small volume,
Not small. Yeah. Globally on Earth.
Okay. On globally, yeah, it's constant.
It is a steady state condition. Yeah. Water cycle, global water cycle is a steady state. Therefore, you can say that what is the total amount of evaporation, transpiration, then stimulation, any output in total equals to all of the inputs, which is precipitation in the form of hail or snow or rain or other things. And this, either this one for a small catchment, as Jeren said, or considering the ds over dt equal to 0 for globe, can be used to solve so many problems. In general, this equation is called water balance, or use, if you, is there someone already passed fluid mechanics in this course? No, you don't pass it. In fluid mechanics, we have Q input equals to Q output always, or not always, generally we use it. And in that course, what we said for that equation, Jeren, do you remember?
Continuity.
Continuity equation, yeah. Now you can link those three things together. Let me link, and this is very important point. Continuity equation or water balance is nothing than conservation of mass. Just this. Continuity equation, water balance is conservation of mass, and we use it. And generally, when we say continuity equation, we assume the system is steady, there is no leakage or output, therefore leakage or extra input to the pipe. What comes in a section of a pipe goes out of the section. What comes? Flow rate, which is called discharge. Okay, so here you see another example that tries to use water balance to solve a problem. Let's see together. A reservoir has a following. This is a reservoir, okay? For a dam, a reservoir. A reservoir has the following inflows and outflows. What is the inflow for this reservoir? It should given. Inflow is the runoff, stream flow that comes from the catchment. The water which comes from the catchment, from the river, it is called inflow. Here you see outflow. Outflow, that we have outflow. And the question says that a reservoir has the following inflows and outflows for several months. Inflow at January, February, and March given. For what is the unit? Cubic per meters. For cubic meter, yeah, you see in terms of volume, not discharge. It gives in terms of volume. Cubic meters at February 6, at March 9. If the storage at the beginning of the January, storage amount of water that we have in the reservoir at the beginning is 60 cubic meters. Determine the storage at the end of March. What will be happen the amount of water at behind your dam? This is a bit a question that shows you how we can find the amount of water at different times in our reservoir. To calculate or to answer, it says that the amount of storage, it means that storage is change, water will change, yeah? Amount of what will change. And therefore the system is not a steady state. We are going to use to find delta S. But delta T is given for us, yes? What is the delta T? 3 months. 3 months is delta T. And we don't, instead of discharge, the question, look at here, the question gave you volume. Therefore, you don't need to use this version of the water balance. This version will be enough. You can say that input volume minus output volume is the delta S, is the storage. Just simply use it. If you understand really this formula, this question is nothing than a piece of a cake. Just use that formula.
Hocam, can I ask something?
Yes, please.
In which cases we are going to use the formula on the top?
In the case that the question gives you discharge, not volume. It gives, instead of cubic per meter, it says cubic meters, it says cubic meters per second, per day, per month. Therefore, you have discharge, you should multiply by number of months or number of seconds, time, the total time. Then you can use the first question. Thank you for your question. So delta S is equals to input or inflow minus outflow. What is the inflow at 3 months? This is. What's the outflow? This is. So delta S is minus 5 cubic meter. At the beginning, delta S, what does the delta S mean? Mathematically, delta S means S2 minus S1. You see, S2 minus S1. And we found it is minus 5 cubic meter. Therefore, S2 minus 60 beginning, storage at the beginning, equals to minus 5. And S2 is 55 cubic meter. It means that the amount of, or the volume of water at your reservoir after 3 months is 55 cubic meter. Now, easy, yes? It's really easy. So, based on the conservation of mass, we can find how much water we have at different times in our reservoirs. This is one example. So I can continue with catchment, but I think this is the first session and we covered the first 2 weeks of our lectures so far, and I will continue with this part next week. So please go to your activity and do it during the week, and if you have time, go to the catchment section of your book. Get ready for the next session. Any question? No question. Okay, thank you for your attention and see you next week. Bye.
See you, teacher. Goodbye.
See you, teacher.